Hey class. So we're going to be going over lecture 12 now. So this is the start of the new material for exam 2. So let's go ahead and get started with the PowerPoint here. All right. So we've learned ionic compounds and covalent compounds, and we're going to start talking about a little bit more about the covalent compounds, which is really what you're going to be mostly dealing with when you go into Chem 285. So this stuff is pretty important, I think, as far as if you go on and learn Chem 285 as well. Okay, so let's go ahead and start off with a little quiz here. Should be review. Oh, sorry, well, this won't be review. Drawing the Lewis structure would be review, but this is actually a new idea. Okay, so the question is asking what is the angle between the two bonds, right? So this angle that it shows right here. So just if you drew a Lewis structure like this and you looked at this angle, it looks like a 90-degree angle, right? But the angle between those two bonds in methane, or the formula for methane is CH4, right? Angle between those two bonds is actually 109.5-ish. Just say 109, okay? We're gonna just say 109. So 109 degrees, okay? So we're gonna talk about why this is, right? So the problem with electron dot structures or Lewis structures is that they look flat, right? So the angles look like 90 degrees. Or if you drew water like this or like this, it'd look like 90 degrees or 180 degrees, right? But in reality, molecules are three-dimensional. So these drawings kind of help you see it a little better. So this is actually methane, okay? So this is carbon in the middle, and this is hydrogen, 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 okay? So looking at this, it looks like 90-degree angles, but when you see it in more of a three-dimensional view, you can see that this angle is actually a lot greater than 90. It's 109 degrees, okay? All right. And then with water, okay, it looks like they're 90 degrees, but this is your oxygen, and then you have hydrogen, hydrogen. So you can see that that angle is actually about 109 degrees as well. Okay, and we'll talk about how to predict bond angles from a Lewis structure. So this is called valence shell electron pair repulsion theory. Sometimes you'll just hear, sometimes people say Vesper. I say Vesper because it's easier, but probably hear me refer to it as the Vesper theory. So this theory just says that the electron clouds want to get as far apart from each other as they can. So if you look at like the example we looked at before with carbon, okay, so around each atom is electrons, right? So around each hydrogen is an electron cloud, and these want to get as far apart away from each other as possible. So around carbon, 4 different groups, the furthest apart they can get is 109 degrees. If they start to go more in a certain direction, then they get closer to another electron cloud. It's kind of hard to see with in 3 dimensions in your head, but 109 degrees is as far apart away from each other as they can get. So this is the lowest amount of repulsion, right? The lowest potential energy. So the molecule is more stable like this. And this is what determines the geometry around the central atom, okay? So here's some basic or common shapes that you'll see. So if you have a central atom with 6 different groups around it, okay, it's referred to as octahedral. If it has 5 different electron clouds around it, again, these are atoms, right? So a single bond or an atom would count as 1 electron cloud. So each fluorine here counts as, or each bond here counts as 1 electron cloud. So a total of 5 electron clouds. And it's called trigonal bipyramidal or trigonal bipyramidal. Four groups, like we saw with methane, is called tetrahedral, and those are 109-degree angles, right? This one's really hard to see flat, but basically these fluorines are surrounding it like almost like a belt. And then you could look at this fluorine, and this one is like the head and the toe. So hard to see there. This one, you have these fluorines around an angle as well. And then this fluorine is actually 90 degrees to that fluorine right there. Okay, so these ones are going straight up and down, and these ones are around the side, and that's just the optimum distance, right, that they can get away from each other. Tetrahedral, they're all equal, 109 degrees between any two electron clouds here. When there's 3 electron clouds, it is actually flat in this case, and so this would just be like dividing a circle up into 3. You have 3 sections of 120 degrees. Okay, so this one actually is flat, and it's called trigonoplanar. And then with 2, also flat, you have 180 degrees between the 2 electron clouds, and that one's called linear, right? Looks like a line. So you need to know these 5 different shapes and how to determine them from a Lewis structure. Okay. All right. So go ahead and try and do this one here. Okay, so in the previous problem, we talked about how each bond is an electron cloud. So this is one electron cloud right here. This is another electron cloud. A lone pair also counts as one electron cloud. Okay, so 2 bonds and 2 lone pairs would be a total of 4 electron clouds. And we'll talk about even more about specifically what counts as an electron cloud. Okay. All right, so 4 electron clouds around this oxygen, right, from the example before. So we're gonna predict, right, or not predict, but know that this is a tetrahedral shape, right? We talked about if there's 4 electron clouds, it's tetrahedral, and each angle is 109 degrees, okay? This is kind of showing like a bond to the lone pairs just to illustrate it, but you know, it's really just has a big electron cloud kind of sitting out like this for the lone pairs, okay? But anyway, those are 190 degrees away from each other. So the molecular shape of water is actually called bent. So tetrahedral is kind of the electron geometry around it, right? Where the electrons clouds are, but molecular shape actually only refers to the shape of the atoms. Okay, so I think I have an illustration that will show this a little bit better. Okay, so we're talking about what counts as an electron cloud. Okay, so lone pairs count, single bonds count, a double bond counts as 1 electron cloud. So this carbon right here has 2 electron clouds around it. Okay, it has this double bond, and it has that double bond. Okay, a triple bond also counts as 1 electron cloud. So this triple bond is 1, that single bond is 1, so this carbon has 2 electron clouds around it. So each of these is a linear electron geometry. Okay. Lone pairs, yeah, they only count if they're on the central atom, right? So these lone pairs don't count as an electron group around carbon. They would only count as an electron group around oxygen. So when you're talking about shape, it's not referring to a whole molecule. It's referring to the shape or the geometry around a single atom, okay? So if I redraw this, this is carbon dioxide, okay? There's 2 electron groups around carbon. So the shape around carbon is linear, okay? And then there's 2 sets of lone pairs on each oxygen. So the shape around this oxygen is actually, the electron geometry is trigonoplanar because there's 3 electron groups around that oxygen. Okay, each lone pair is 1 electron cloud. So here's another example, sulfur dioxide. There is 3 electron groups around this sulfur. So this would be a trigonoplanar electron geometry. And there's 120 degrees between those electron groups. So I've thrown out two different terms. There's electronic geometry or electron geometry, and then there's molecular shape. Electron geometry is only concerned with bond angles and has to do with the number of electron clouds. Okay. So here there's 3 electron clouds around sulfur. So this is a trigonal planar electron geometry. We don't really care what the electron clouds are. They could be double bonds, single bonds, lone pairs, right? Doesn't matter. There's 3 of them. And all we look at for electron geometry is how many electron clouds are around that central atom there. Molecular shape is when we actually do care. We ignore lone pairs for molecular shape. So if you look at this sulfur dioxide, if you take away the lone pairs here, then really what you have is this shape like this. And that shape, you see that shape, it's referred to as bent, okay? So we'll see a couple different shapes here in these charts coming up. Okay, so if there's 2 or 3 electron groups, okay, so electron groups is here. Okay, so if there's 2 electron groups, you have one option. It's just linear, right? It's going to be flat across. You're not really going to have any lone pairs on a central atom if there's only 2 electron groups. So there's 2 bonded atoms and 0 lone pairs with 2 electron groups. And the molecular shape is linear, and there's the electron group geometry or electron geometry or electronic geometry is linear, okay? With 3 electron groups, electron group geometry only depends on electron groups, so that's going to be trigonal planar. Okay, and if there are 0 lone pairs, then we look at the shape here between all the different atoms, right? And you still have that trigonal planar shape, so the molecular shape is also trigonal planar. Okay. In this example, we have 3 electron groups, so it's trigonal planar, right? We don't care what the electron groups are here. Trigonal planar because there's 3 of them. Now, if you have 1 lone pair, so this is saying we have 1 lone pair, okay? So you can imagine a lone pair on this right here. If we ignore the lone pair, we get this shape, which is bent, okay? All right, so hopefully you're seeing a trend here. So let's say you have 4 electron groups. There's 3 possibilities here. Okay, so if we have 4 electron groups and 0 lone pairs, so all 4 of the groups attached to the central atom are atoms and they're not lone pairs, then the overall shape also looks like a tetrahedral shape, okay? Again, 4 electron groups here, it's tetrahedral, okay? Electron group geometry is only determined by the number of electron groups. But then if we have 1 lone pair, if we had a lone pair up here, but we decide not to look at it, then the shape we have is actually kind of a pyramid outline, right? So it's trigonal pyramidal, trigonal pyramidal. Electron groups, there's 4, again, automatically tetrahedral if there's 4 electron groups. But in the case of water, we have 2 sets of lone pairs on the oxygen. So if we ignore those and just look at the shape of the atoms that are connected, we get that shape again, which is the bent shape, okay? So you need to know for electron groups up to 6 electron groups, right? So 2 electron groups is linear, 3 is trigonal planar, 4 is tetrahedral, 5 is trigonal bipyramidal, 6 is octahedral. So those are the electron groups, or the electron group geometries you need to know, which were in the previous slide. For molecular shape, you just need to know the ones on these 2 slides. So it can either be linear, trigonal planar, with the trigonal planar. So, sorry, linear has the option of linear, that's it. Trigonal planar has the option of trigonal planar, or if there's a lone pair, then it's bent. Tetrahedral has just tetrahedral, or if there's 1 lone pair, trigonal pyramidal. If there's 2 lone pairs, then you'd have a bent, okay? You could memorize this chart if you want. I think it's easier just to like look at it without lone pairs and see what shape it is. But up to you how you want to go about doing that. And then also just know the bond angles. And the bond angle is determined by the electron group geometry. So it doesn't matter if it's bent or trigonal parameter or whatever. The angle is actually determined by the total number of electron groups. So for tetrahedral, it's always 109. For trigonal planar, it's always 120. And for linear, it's always 180. Okay. All right, go ahead and pause the video and try and do this one on your own here. All right, let's go over it. So for this one, you don't have a Lewis structure to go off of, right? And if you try and do it in your head, it might be a little difficult, but hopefully at this point you've worked on Lewis structures. So if I'm doing the Lewis structure for this guy here, I'm going to draw all my atoms with their valence electrons. This is the Lego approach that we talked about. Okay, and then we just connect the dots basically. Okay, so that would be my Lewis structure for PCl3. So if the question asks for the shape of PCl3 and it doesn't indicate which atom you're looking for the shape of, then it really refers to the central atom here. Okay, so this P right here. So you can kind of just assume it's the central unless the question for some reason said what's the shape around chlorine or something like that. Okay, but since we're looking at the central atom here, there are 4 electron groups, right? We have a lone pair, which counts as 1. We have this bond counts as 1, that bond counts as 1, and that bond counts as 1. So the electron group geometry would be, I can't see here, would be tetrahedral. Okay. So now the question is asking for the shape, okay, which would be the shape or the molecular shape. And in this case, we need to ignore the lone pair, right? So if we ignored the lone pair, this would look somewhat like a pyramid with a triangle base. Sorry, I'm kind of drawing all over it, but hopefully you can see the pyramid there. A little drawing. Okay, so this is a trigonal pyramid, or it should be an O, trigonal pyramidal. Tell I'm so good at pronouncing these. Okay, trigonal pyramidal. Cool. All right. Or if you just memorize the list, then you could say it's tetrahedral with 1 lone pair, so it's trigonal pyramidal. Okay. All right, well, let's go through some examples here. So the first step for all these is just going to be to draw out the Lewis structure. So for ammonium, that would be the Lewis structure that we have. And ammonium has 4 single bonds, so that's 4 electron groups. 4 electron groups. So that would be tetrahedral electron group geometry, okay? And because there are 0 lone pairs, the molecular shape is going to be the same as the electron group geometry here, which is tetrahedral. And the angle between them is 109 degrees. Okay, for sulfite, if we drew this out, we would get 1 lone pair and 3 single bonds around sulfur, which means we have 4 electron groups again. 4 electron groups. So we would imagine that our electron group geometry would be tetrahedral, okay? But if we took away the lone pair here, we actually have a trigonal pyramidal shape. Ooh, look at that. Okay, so the electron group geometry is tetrahedral with a trigonal pyramidal shape because there's 1 lone pair. Okay. Carbonate, draw out the Lewis structure for that. Oh, it gave us all the answers at once. Okay, there's 3 electron groups around carbon. This double bond counts as 1 electron group. This single bond is 1, and that one is 1 as well. So 3 electron groups would give us a trigonal planar electron geometry. And then if we ignore lone pairs, well, there's no pairs on the carbon. So because there's no lone pairs, the electron geometry and the shape are going to be the same. They're both trigonal planar. Okay. Okay, so if we look at acetate, this is a harder one to draw out. But drawing out the Lewis structure, you get this. Okay. Now this one would be really hard if the test just said, what's the shape of acetate? Because there's kind of two central atoms here, right? You have this carbon and that carbon. So if we looked at the first carbon, we have 4 electron groups around it. So that would be tetrahedral electron geometry. And since there's no lone pairs, the shape is also tetrahedral. And then this carbon here has 3 electron groups around it, 1, 2, 3. And since there's no lone pairs, the molecular shape is also trigonal planar, okay? And these are the bond angles that associate with those. Cool. All right. So that's our lecture on molecular shape. Hopefully that was, hopefully made sense. And just the only things you need to know are the shapes that were listed in the PowerPoint. If you look up tables on Google or maybe even in your book, you're going to find some really funny, as you get bigger molecules, some really funny shapes and stuff like that, with some cool names. But the ones that you only need to know for the test are going to be the ones that were in the PowerPoint here. So all right, have fun learning that, and we'll catch you next time.